and it is called calorimetry. Okay, so the other day, last day in class, we learned that heat flows from areas of high heat to areas of low heat until something called thermodynamic equilibrium occurs. So now we're going to talk a little bit more about what thermodynamic equilibrium is. Equilibrium is a word that means that things are in a steady state. It doesn't mean that your molecules are not moving, because the only time that molecules stop moving is at absolute zero. And so that's not what we're referring to. What we're referring to is the state where as soon as products are made, some other products are converted back to reactants. And so the changing is still always going on, which is why we oftentimes refer to this as a dynamic equilibrium. So dynamic means always changing. But equilibrium means that we don't observe any change that's taking place. It's not observable to us because we are not at the molecular level. We can't see those things happening. And so we have to assume that if what we perceive as chemists, as the observers of these chemical reactions, if what we perceive is no change, that doesn't necessarily mean that our system is dead or that the molecules have stopped moving. It just means that as one thing is converted, something else is converted right back. And so it's this cycle that just doesn't look like it's moving at all, but still is. Okay, so how does thermodynamic equilibrium differ? Thermodynamic equilibrium talks about the movement of heat. You have all already experienced thermodynamic equilibrium in your lives before. If you've ever put a piece of ice into some kind of liquid, doesn't matter if the liquid is hot or room temperature or cold, you have witnessed thermodynamic equilibrium. Over time, what happens to the ice cube? It melts. What you're observing is called thermodynamic equilibrium. So, the main principle of this concept is that heat will transfer always from the hotter substance to the cooler substance. Heat will transfer always from higher heat to lower heat until both substances have the same temperature. Heat will transfer always from high heat to low heat until both substances have the same temperature. And so that's what is happening when you put ice in a liquid. It doesn't matter how long it takes, the ice will melt. And it'll melt, it'll keep transferring until the ice that now becomes water is at the same temperature as the original liquid before the ice. Okay, so then what will happen is that the hot substance gets cooler, but the colder substance, what will happen to that? It'll get warmer, yes, that's a better word for it. And the temperature of both of these things is the same. Okay, so what in the degrees Celsius is the temperature of ice? So 0 degrees Celsius. The temperature of, like, let's say it's room temperature water. Room temperature in degrees Celsius, a warm room would be 25 degrees Celsius. So that means that when thermodynamic equilibrium is reached in this system between the ice cube and the room temperature water, that T final, let's see, the final temperature is the temperature at which both substances exist. That's the same for both substances. In this case, the ice cube and the water. That T final is going to be somewhere in between 0 and 25 degrees. It can't be less than 0 because that's the coldest thing in your system. And it can't be more than 25 because that's the warmest thing in your system. So T final will be somewhere between 0 degrees Celsius and 25 degrees Celsius. But where? Like how far in between? Will it be closer to the 0 or closer to the 25? It depends on your substances. And so there is a lovely formula that's going to help us to determine where that final temperature will be at. Okay, so this looks complicated. This is the easiest it'll be. It's a Q. Okay, so do you remember from last time what Q stands for? Heat. Heat is a quantity that is a measure of energy. And so because of that, it is either measured in joules or kilojoules. M in this case is the mass of your object. Most of the time, you will be measuring that mass in grams. This is different than it is in physics. We always measure things in kilograms in physics. In chemistry, we don't. We use grams. Delta T stands for, do you remember what triangle means, or that delta, do you remember what that stands for, what words? Change in. So we need to figure out what the change in the temperature is. How do we calculate change in temperature? It is always final minus initial. So I guess I'm using physics terminology here. It doesn't matter how you write initial. Usually in chemistry we do little I, final minus initial. In physics we use final minus like naught for 0 because that's the temperature at the 0, at like time equals 0. I just was in physics mode, so that's why I wrote it down like this. Mostly you'll see me write it like this. They mean the same thing. But now C is a thing that we've never heard before. C is a special thing. It's called the specific heat capacity. And it's unique for every substance. So before we start talking about the different values for C, they are constants, and so the specific heat capacity for water is always the same number. For aluminum, it's always the same number. And on your new sheet, there'll be a table there that gives you all of these. This is something that you'll find by looking at your gray sheet. That's the new color of sheet. I'll give that to you in a moment. But let's just talk about what specific heat capacity actually is. It is, let's write it here, the amount of energy required to change 1 gram of whatever the substance is by 1 degrees Celsius. You already have some practical experience with specific heat capacity, and you don't even know it. Okay, so that's its technical definition, but what is it really? A substance with high C, or high specific heat capacity, I just don't want to write those words out anymore. A substance with high specific heat capacity is something that requires a lot of energy to either warm or cool the substance. And the reason I tell you that you already have experience with this is because when you were little and it was a hot summer day, did you ever have a little kid pool?
Yes, I still do.
Okay, oh, you still do. Wonderful. So what happens when you fill up your little kid pool? You use the hose from the faucet on the outside, right? And that water is coming out of the ground at whatever temperature those pipes are at under the ground, which is usually considerably cooler than the air temperature. And so what would that temperature be? It's probably in the 60s. What happened to you when you filled your pool and you first jumped into it on the hot summer day? Do you remember what it felt like? It was really cold. And then it takes, even if it's a hot day, it takes a long time for that pool to be warm enough for you to like actually swim in it, right? That's because water has one of the highest specific heat capacities. This is why when you are wanting to go swimming in the lake, it just is so much colder than the air temperature, even if it's been warm for a considerably long period of time, because the lake is a pretty big body of water, but also water just takes so much energy to heat or cool it. You also have experience with this if you've ever put something in the oven in like tin foil, or I guess aluminum foil, more properly speaking. You can touch that aluminum foil like right away. Like you pull it out of the oven and then it sits out on your stove or on your countertop for like 30 seconds, and it is cool enough to the touch that you won't burn yourself. That's because aluminum has a really low specific heat capacity. So it doesn't take a lot of energy at all to heat or to cool it. So depending on the substance's specific heat capacity, if you put something in water that's hot, it won't change the temperature of the water a lot, but depending on what you put into the water, that substance might change temperature quite drastically. You're welcome. So what I'm handing out to you now is what is called the gray sheet. And because the lights are pretty dim in here, it's going to look like regular paper. But if you hold it up to your white notebook paper, you'll see that it is gray actually. Okay, so the first side of this sheet has a bunch of formulas. The very first formula that you'll see is the one that is on the board right now. And then there's a whole box with all of this nonsense stuff. We'll get to this in a minute. The very bottom table just gives you some common substances and their specific heat capacities. So what is the thing on this table that has the highest? It's water. What substance has the lowest specific heat capacity? It's lead. So that means that lead will be the first to get hot and it'll be the first to get cold. Water will be the last to get hot or cold. So when you need to use this formula and you need to find C, if you know the identity of your substance, you can find it here. But now this is really important, so listen carefully. If you don't know the identity of your substance, solve for C and find it on here. And so like you can solve the mystery of what your substance is by solving this equation for C and then looking on here. And if it's close to one of those things, that's probably what it is. This is not all of these are not all of the specific heat capacities that we know. Those are just the most common things. So hopefully I don't ask you a question that requires anything other than these, although you can just very easily Google that information as well. The back side has a very complicated looking table. You won't know how to do this until next week. So just hang on to this sheet for now. I'll explain this when we get to enthalpy of formation, but just to save paper, I put them all on one. Okay, so this is the most basic way of using this formula. This works if you have only one substance. Okay, so just for fun, you probably are going to want to have the algebra to solve this formula for the other permutations. Like, so if you're looking for the heat associated with a process, that's Q. Your formula is already solved for that. If you need to find M, your formula will look like this: Q divided by C times delta T. If you're solving for C, your formula will be Q equals M times delta, or Q divided by M times delta T. And remember that delta T it equals, maybe this is something you want to write on there, T final minus T initial. Okay, this works great for if you have one substance. I'm not going to do it because I think you can do it yourselves, but maybe make a note to yourself. Questions 7 through 10 use a form of this formula. So it might be solving for Q, it might be M, or it might be C. If it says to you, like in number 10 on your homework, calculate the amount of energy required, that's Q. Yes, Mason?
So if we have a problem and we're given a certain amount of energy to heat the thing, when we do the equation, will it be in joules or will it be in kilojoules?
It'll be in joules.
Okay.
Because your formula, the unit for specific heat capacity is in joules.
Yeah.
And so also, you'll use degrees Celsius here. So this is one of the very only times that you're going to use degrees Celsius in your math. Okay, so this works, again, only when you have one substance. What happens when you have more than one substance, though? That's when you need the calorimeter. Do I still have any? I do. What's a calorimeter? It's a chemistry thermos. So if you have an insulated water bottle at your desk right now, you have a calorimeter. A calorimeter is a device that is meant to keep heat from the surroundings from entering the reaction or vice versa. It's meant to keep, so So it's a thermos. It's meant to keep hot things hot and cold things cold because it doesn't allow the energy to like get into it. So this is a calorimeter that we would use in real life. It's a thermos or an insulated water bottle. This is what a calorimeter looks like in chemistry. It's got this is what your water bottles look like on the inside. There is an outer ring that's made of a metal. And then because your water bottles shouldn't come apart, there's a second layer of metal. And in between those layers of metal is some kind of, like, it's filled with air, some kind of barrier to prevent the heat from coming through the walls of the metal. And so here we have a styrofoam cup. Your water bottles are not made of styrofoam, but this is just to be an even better insulator. So there's this like layer of styrofoam, which is a very good insulator. It doesn't let heat in or out. That's why it's used in your like takeout boxes. My brother actually is afraid of the sound and the feel of styrofoam. You know how well, this stuff doesn't really because it's like pretty thick. You know how like has that like squeaky? He can't stand the sound of it, and if like he touches it, he gets really creeped out by it. He's afraid of styrofoam. And then it has a second layer, which your water bottles do as well. And this inside this second container is where the reaction takes place. The calorimeter also comes with a top, just like your water bottle does. Most water bottle tops are not insulated. They're made of plastic, which is a poor insulator. And so if you've ever noticed on a very humid day, if you put water and ice in here, like the top of this part of the water bottle will get all sweaty. That's because that part isn't insulated, and this isn't either. So what is this wacky thing? This is a stir stick that comes with it. So you can like spin this on the outside without taking the lid off. And so you can mix up your reaction by doing this without having to take the lid off. It's got this cork that's fitted in as a stopper, and it's pretty old. Like I would say this predates my existence, which is old. And so I'm not even going to attempt to take it out. But then this has a hole. The hole is for a thermometer so that you can measure that change in temperature. So how would we use this? We would pour one thing in here, measure the initial temperature, pour another thing in. Maybe that's a piece of metal. Maybe it's a chemical reaction that we're going to observe. Doesn't matter. And then we're going to measure the temperature after it doesn't change anymore, after it reaches thermodynamic equilibrium. So that's what a calorimeter is. It's basically a chemistry thermos. So it's just used to keep the surroundings and the system very separate. They're not perfect, just like anything in the laboratory. They're not perfect, but they're pretty good. If you feel like anything hot on the outside of here, you know you've got something bad. But that would be like a regular coffee cup. They feel hot to the touch. Okay, so when we're using a calorimeter, we will use this equation. The heat, that's a 1. The heat associated with substance 1 is going to equal the opposite sign of the heat associated with substance 2. Why the negative? One of these substances gets hotter, and so that would be an endothermic process. What's the sign on an endothermic process? It's plus. One of the substances gets colder. That's exothermic. What's the sign on an exothermic reaction? Negative. And so the negative there will help us to keep track of which is the substance that's gaining energy and which is the substance that's losing it. Okay, so if this relationship is true, this relationship is also true. Okay, so this is a little bit of algebra here. I already know that Q is equal to M times C times delta T. And so if Q1, if we have Q1, that means we also have M1, C1, delta T1. So Q1 is equal to M1, C1, delta T1. I just put this relationship in for Q, and so I'm going to say M1, C1, delta T1. The same thing applies on the second side of the reaction, or the equation rather. I have that negative there, so that's going to help me to account for the fact that one of these processes will lose energy. That's the exothermic process. Okay, so we're going to use this formula or a form of it to figure out all of the information for when we put two substances together and they are going to transfer heat until thermodynamic equilibrium is reached. There's nothing really super complicated about these except that the math is a little bit hairy. So I did solve all of these problems, or all of these equations for you. And so on your gray sheet, all you need to do is make yourself a very tidy data table. Then you can choose which one of these equations from here you need to select. You need a tidy data table because there's going to be a whole lot of stuff going on. Look at how many variables there are in all of these equations. You need to be able to keep track of all of that information when a problem comes along. So let's do number 11 as an example of how to use the gray sheet for this kind of work. I'm going to say it again and probably 3 more times before I'm done here. If you don't make a data table, you are absolutely cooked. And so this is one of the reasons that in the earlier, easier stuff, I made you make a data table for everything, because if you don't do it now, there's no way. There's no way other than luck. And we are chemists, we are not magicians. Okay, so what I'm going to do is just read through my data, and when I find information that I think should go in a data table, I'm going to write that down. I already know from looking at my problems, from looking at my equations on here, that I'm going to need 2 M's, 2 C's, and as many as 3 T's. The reason we only need 3 T's and not 4 is because T final for substance 1 is equal to T final for substance 2. That's like the whole point of the calorimetry, is that we get to that end point where the substance or both substances have the same temperature. So I suppose if you know that this is a calorimetry problem, you could start by doing this, T initial 1, because you're going to need all this information. And then the last thing that you need is TF. TF is the same for both things. You could do this, or you can just make them up as you go. I don't know which is easier for you. I guess I like this format because then I know I have to find all of this stuff. Okay, so looking at my homework then, number 11 says, an unknown mass of copper. Okay, so right away I know what question mark is. Question mark is M1. How do I know it's M1 and not M2? Well, it doesn't really matter. But because it's the first mass I'm hearing about in this problem, I'm calling it M1. But I know that it's the mass of copper. So now every time I see something about copper, that has to have a little 1 next to it. So I'm just going to write copper right there just so that I can keep track of that. Now, if I wanted to fill in C1 right away, I can by looking at my gray sheet and just finding copper on there. Copper is 0.385. The unit there is the same unit for everything, joules per grams times degrees Celsius. Okay, so then I'm going to continue on reading my problem. It says that is placed into 50.0 grams of water. Oh, my bad. The unknown mass of copper is at 75 degrees Celsius.
I think that's from the gray sheet.
75 degrees Celsius is the initial temperature of my copper. How do I know? It says that unknown mass of copper at 75 degrees Celsius. Now, if that's placed into 50 grams of water, that's a mass. And since there's only one other mass line left, it's got to be mass 2. That water has a temperature of 21.3 degrees. That's T initial 2. My question says the final temperature of the system is 29.5 degrees Celsius. What is the mass of the copper? Okay, so where do I find that missing bit of data in my data table? Elliot? On the gray sheet. Water is 4.18. And your unit for that is the same as it is always. What? I heard somebody say what? Do you see where I got that from? Actually, I know that one off the top of my mind. That's the only one I know, but you just use it so much. All right, so which one of the formulas from the gray sheet do we need? The M1 one. Okay, so write that formula from your gray sheet down just like you've always done. Oops. C1 delta T1. What's your next step? Mason. Put numbers into the formula. Okay, so I'm just gonna make this a little smaller because I'm gonna run out of room here. Don't forget the negative symbol that has to go with. Otherwise, you'll get a negative mass at the end of the problem, which is illogical. So that's how you'll know that, oh, I forgot my negative. M2 is 50. C2 is the 4.180. How do we find delta T2? How do you find delta? Ray?
Final minus initial.
The final is the same for both of them. But T2 initial is the 21.3 degrees Celsius. C1 I found on my gray sheet, it's the 0.385.
Can we solve for can we find delta T before?
You can find delta T beforehand. If you want to put that in your data table instead, that's totally fine. It's the same amount of work, really. Oh, do you see what I did wrong here? I started doing initial minus final, and that's very bad. You want to do final minus initial, and so that final has to be the same for both. Now you're going to put this into your calculator. My friends, if you do not do order of operations with parentheses on your calculator, you will never get the right answer. So you need to type in 50.0, easy, times 4.180, easy. And now, before you do this math, the subtracting, hit a parentheses. 29.5 minus 21.3. So if you don't have parentheses here, your calculator will think multiply by this number and then subtract this from everything. Not good. Now you can press enter if you want, but what you should, if you do press enter, you should get this.
Yep.
Good. Now you're going to press divide, and whenever you're doing anything dividing by more than one number, you want a parentheses here. But if you're the kind of person who puts parentheses in your calculator, you need 2 of them.
What?
Because otherwise your calculator won't know what you mean. So if you're going to put a parenthesis here, you need 2 of them at the start. So whenever you press divide, always put an extra one in. You don't have to close it, you just need to open it. So then if you're going to put that parentheses there, that's fine. Otherwise just press times, but then you need another one here. Like this one is essential. This one is not necessary, but this one is. And then you don't even need to close any of them. Okay, so then as my denominator, if I press enter now, oops, I'm sorry, no, because I did this all in one step. You should get, did you get the negative? If you got the negative, that's because I did too. I didn't take into account this negative here. So if you get a negative, you're solving for mass, it can't be negative. This is not antimatter. So just make it positive by putting a line through it and call it good.
I got 98.92.
Okay, let's see.
I got 96. What's the label?
You're solving for mass, so what's your unit for mass? Grams. Okay, so we've got a couple of different calculator problems. If you didn't,
I know why.
do you? Okay. If you did not get exactly this, let me look at your calculator so I can determine where your math is wrong. Because it's a typing issue. It's a calculator failure. Any questions about how I got this? As long as you get this part right, and you know how to use your calculator, you're in business. But that's why this is so essential, and why when you were doing little baby problems back in the olden days when things were easy, I made you write that to get you into the habit of doing it so that you can do it here. All of the rest of the problems on this homework are exactly the same. You're not always going to choose this formula, but if you know how to make your data table, you'll be good to go. All right, you have the rest of the time, that's half an hour, to work on this. How many of you are not going to be here on Friday?
I don't know yet, but I don't want to know.
Okay, I am going to, I'm going to work on getting you, I was supposed to do that and I forgot. I'll work on getting you the lab that we're doing on Tuesday of next week. Friday will be a work day so that because this homework is lengthy. I want you to have opportunity to check your work as well. So there'll be a lab for you to write up and this homework to do on Friday. You want to make a cameo?
Hey, man.